page is just strictly review. I just want to do it by calculator command because we've done a million examples like that already, and then I want to move on. It says a 1997 study by Gelber and colleagues found a mean heart rate variation of 49.7 with a standard deviation of 23.4 in 580 normal healthy adults. What proportion of individuals can be expected to have a heart rate variation between 27 and 73 beats per minute, assuming a normal distribution? So this is just review. So this is page 1 of lecture 4. It says X is normal with mean 49.7 and sigma equals 23.4. What proportion of individuals can be expected to have a heart rate between 27 and 73? So find the probability that X lies between 27 and 73. That's the question, right? So we know how to do this, don't we? This is about 1x, right? The question is about 1. So I'm going to use z equal x minus mu over sigma if I'm doing it by hand. If I'm doing it on the calculator, I'm going to say norm CDF, left endpoint 27, right endpoint 73, mu is 49.7, and sigma is 23.4. That's it, right? It's about 1, so there's no reason to do sigma over rad n, just sigma. N is 1, right? So even if you did sigma over radical n, n is 1. So it would still boil down to that. And part B, if repeated samples of 6 individuals are randomly selected, what proportion will have a mean heart rate between 27 and 73? So probability 27 less than x bar 6 less than 73. So this time I'm using, it's about the mean of a sample of size 6. So I'm using z equals x bar minus mu over sigma over rad n, right? So this would be norm CDF, 27, 73, 49.7, and sigma over radical 6. You get it? It's all review. Is there any question regarding this? Yes?
So in this case, if you're doing it by hand, is the x bar 6, right?
This one?
Yeah.
Then I would be turning both of these into z's by going 27 minus the mean, 49.7, divided by 23.4 over rad 6. And then do the same thing for the 73. Get it? Any question regarding this? Okay, if there is no question, then let's go to confidence intervals. let's say that you have a population of size n, and you don't know mu. Mu is unknown. The population mean is unknown. What's the next best thing to the population mean? If I don't know the population mean, what am I going to look at? What does inferential statistics tell us to do? If you don't know the population mean, what do you look at? What do you think? Suppose I'm looking for your mean age, and I don't know what it is. Mu, unknown. What shall I do? Can I take a, yes? Median? I could, but I want to use inferential statistics. Yes? Yeah. I take a sample. I don't know mu, so I take a sample of size little n, and x bar n, which is the sample average, will serve as a point estimate for mu. The sample average serves as a point estimate for the population average. Does that make sense? So maybe I'll take a sample of size 10 from amongst you folks, and then I will observe the average x bar 10, and then whatever x bar 10 is, that's my estimate for mu. Agree? So that's the first thing you have to know. First thing you have to know is that this is a point estimate for mu, which means that it's one number that estimates the population mean. And this is the sample average, is a point estimate for mu. So that's the first way to estimate mu. That's the first way. The second way to estimate mu is by an interval estimate. Not a point estimate, but an interval estimate. That's the second method of estimating mu. So I'm looking for an interval like this, a comma b, such that I am a certain percent confident that mu lies in this interval. And this number can vary. I could be 98% confident, 90%, 99%, right? So the confidence level can vary. So I'm looking for an interval estimate such that I am blank percent confident that mu lies in this interval. Wouldn't you agree with me that this interval needs to be a small interval? Confidence interval should be narrow. That's the first thing. And second thing is that the confidence level should be rather high. Let me explain what I mean by that. would it be helpful for me to say to you, the mean age in this class is between 15 and 25? Is that helpful? After all, I'm looking to hone in on mu, right? I'm looking to zero in on mu. So is that helpful to you? Does that give you any information? Not a lot, right? Wouldn't it be much better if I could say that the interval, the confidence interval for mu lies between 18.1 years and 19.8 years. You see how that interval got small and I am able to zero in on mu? So that's what I mean by the confidence interval should be narrow. Such a big interval is not helpful to me, right? And the confidence level should be rather high. I'm not interested in being 40% confident or 60% confident. I want to be rather confident that my mu lies between 18.1 and 19.8, right? So this confidence level should be rather high. 90%, 95%, 99%, like that, okay? Unfortunately, let me write on the next page so that doesn't get chopped. Unfortunately, as the confidence level goes up, the confidence interval gets wider. So I'm trying to keep the confidence level up, but the interval just got wider. And I don't want it to be wide, but it's a trade-off. So this is a trade-off. There's a trade-off between the confidence level and the size, right? As soon as the confidence level goes up, unfortunately it gets wider. Not that I want it to be wider. Okay, so without further ado, I would like to show you the formula for the confidence interval so that you have a question? I'm going to explain that. I'm going to explain that to you. Why it gets wider, I'm going to explain. So instead of getting all caught up in the derivation of it right now, I want to get to the formula so that you see what we're dealing with and how you have to implement the formula. And then I'll go back and fill in all the gaps, okay? So here is the formula, and you will see this formula on the bottom of page 2. So a 1 minus one minus alpha confidence interval for mu is given by the following: x bar n plus or minus z alpha over 2 sigma over rad n. That's the formula. You see this formula on the bottom of page 2. You see this plus or minus? It's written out twice in your notes. If you use the minus, it gives you the left endpoint. If you use the plus, it gives you the right endpoint. After all, you know I'm looking for a comma b, right? So a is given by using the negative, the minus. B will be gotten by using the plus. Does that make sense? Okay, so what's going on here? Let's see. I want to do an example before anything else so that you see how it works. Let's say that I'm looking for the 80% confidence interval for mu. which is unknown. Obviously mu is unknown. Otherwise, why would I be searching for an interval, right? Mu is unknown. So I take a sample. The sample is of size 40. And I see that the sample mean x bar 40 is 100. I'm just making up these numbers. And it is known that sigma for the population is 4. It's given. Sigma x is given. Find the 80% CI for mu. That's the question. So first of all, I see that this guy is the point estimate, right? What is a point estimate? It's one number that estimates mu. The sample average is always the point estimate for mu. So I'm going to plug into that formula. But before I can do that, what I do is take the confidence level that they give you and simply put that confidence level in the middle of your Z distribution. So take your Z distribution. Because they want the 80% CI from you, take this 80 and put it in here, 0.8. That means that 20% is left to be shared between the two tails, right? Total 20. So 10 goes here and 10 goes here. That means this is 1 minus alpha. It's the 1 minus alpha CI that I'm looking for. So this is 80%. 1 minus alpha. We know that the total area under the curve is 1, right? So if this is 80, then this sum of the tails is 20, right? So this is alpha over 2, and this is alpha over 2. And all together, I have 100%. So if this is alpha over 2, this is alpha over 2, this is 1 minus alpha, all together I have a total area of 1. Do you see that? Because the sum of these two tails has to be alpha. Sum in the two tails equals alpha area. So each tail is alpha over 2. So this number is called Z alpha over 2. Because that's how we define Z something, right? Z something is defined to be the number such that this area is the area to the right of it in the tail. So this is Z.1. Can we find Z.1? How do we find Z.1? We go to the T-table, right? So go to T-table, last row. For this, what do you see? You must have your T-table. It sure is. 1.282. Go to the T-table last row. Last row because that deals with Z, Z star, right? You remember this from last time, right? So 1.282. Once I have that number, I'm done. It's just plugging in now. Let's go back and finish up this problem. This is given. X bar 40 is 100. Plus or minus. This is the only number that I needed, really. This is the only part that requires any work on my part. Z alpha over 2, which is 1.282. Sigma is given, it's 4. And divided by rad n, rad 40. This part, this whole mess is called E, the margin of sampling error. That's called E, the margin of sampling error. You know this is called standard error, right? Remember from the last time? Just this part is the standard error. If I attach a Z alpha over 2 to it, it's called the margin of sampling error, E. So first I compute my E, and then I add and subtract E to x bar n. This is x bar n, x bar 40. The point estimate. So can you please get me a number for E? .81, do we agree with that? 0.81, okay. So all I have to do is say 100 minus 0.81, which is 99.19, and 100 plus 0.81. 100.81, and that's my final answer. So to interpret this, we say, let me take a new page. We are 80% confident that the true population mean mu lies in this interval, 99.19, 100.81. That's how you interpret that. We are 80% confident that the true population mean mu lies in this interval. Finished. That's how you do confidence intervals. Get it? If I wanted to do a part B, let's call this part A, and let's say that part B says find a 98% CI for mu. All the numbers are the same. All the givens are the same. Find a 98% CI for mu. Look at what changes. Take the 98, stick it in the middle. That means 0.01, 0.01. Agree? That means this is Z 0.01. Can you go to the T table and find me Z 0.01? Please? Do we agree with that number? Beautiful. 2.326. Let me label this Z. So in my old formula, the only number that's going to change is this one. This 1.282 is now going to be replaced by 2.326. Everything else stays the same. You see? X bar is 100 plus or minus 2.326 times sigma over rad n. That's the only number that's going to change. But the reason why I do this example is because I want to illustrate that E got bigger. Remember you were asking me why is it wider? Look, here's now E, the margin of sampling error. Can you find me that E, please? Yeah? 1.47. So now I'm going to go 100 minus 1.47 is the left endpoint, and 100 plus 1.47 is the right endpoint. So 98.53, comma 101.47. It got wider. Do you see? Compare the answers to A and B. The level went up, the interval gets wider because the E gets bigger, because the Z alpha over 2 gets bigger as the confidence level goes up. Because as the confidence level goes up, you're more into the tail of the distribution, and as you get into the tail of the distribution, the Z alpha over 2 is getting bigger, right? Okay. So I want to draw a picture of this confidence interval. I started with X bar n, which was 100. And I went a distance of E to the right and a distance of E to the left. And I ended up with X bar minus E and X bar plus E as the right, as this is the left endpoint A and the right endpoint B. Left, right. That's really what's happening, right? Yes or no? So the length of the confidence interval is 2E, because there are 2 E's here. The length is 2E. Always. Because you're always starting in the X bar and going E, E. So the length is always 2E. Follow? What's your question? Yeah.
Do you ever pay attention to the other side?
Which other side?
It's 0.01 and 0.01.
This is just minus 2.326. That's where this plus or minus comes from.
I see.
Are you okay with this? Let me take it one step further. Okay, I just want to give you all the basics that you need before I start deriving stuff, because that's background, but this is what you would need to do for your test, right? Okay, what if the question was slightly different and it looked like this? Part C. I still want a 98% CI for mu, same as B. The sample, I take a sample of size n equals 40. Let me change the sample size. N equals 20. X bar 20 equals 100. But this time sigma is not known. No sigma. They didn't give me sigma this time. This time, they gave me the raw data from the sample. I took my sample of size 20, and they gave me numbers like 3, 9, 27, 8, like that. So I can find my own X bar for that sample. I found this, let's say. Found X bar 20. Either they gave it to me or I found it. It doesn't matter, because if they don't give it to me, I can take the data and find the mean. And let's say that I found my own S. What is S? It's a sample standard deviation. Let me remind you. It's equal to radical summation xi minus x bar square over n minus 1. Remember, this is due to Bessel's correction. Remember, we divide by n minus 1 when it's a sample. So I can find my own mean and my own S. I'm not going to do this by hand. I'm going to do this on the calculator. But let's say that this is the scenario, okay? So I find my own mean, and I find my own S, and this S turns out to be, I'm going to make up some number, 3. Let's say S is 3. So X bar turns out to be 100, and S turns out to be 3. And I use this formula to find S from the data. You're following me, right? So this time sigma is unknown for the population. So this time the formula is going to be the following. One minus alpha confidence interval for mu is given by x bar n plus or minus T alpha over 2 S over rad n. Do you see that the template is the same as before? Let me put the old formula back up. This used to be the old formula. Oh, where are you, formula? Here. This used to be the old formula. No, it's not here. Where are you? Here. It used to be this. It used to be this, x bar n plus or minus z alpha over 2 sigma over rad n. Now it's t alpha over 2 s over rad n. But once you know this, you kind of know this, because the template is the same. You see? Now, you're not going to go to the last row of the t-table, because S, the sample standard deviation, is based on n minus 1 degrees of freedom. So you will now go to the n minus 1 degrees of freedom row in the t-table, not the last row, because the last row was for z, and you are not dealing with z, you are dealing with t based on n minus 1 degrees of freedom. So I want to finish up this problem to show you how the number would be different. Again, since I'm looking for the 98% CI for mu, here's my problem. I take my 98 and I put it in the middle. Since the total is 100%, this is 0.01 and 0.01. But this time it's not Z, it's T. Because when S is what you're dealing with and not sigma, it's a T distribution. I will write the formula for T in a second. This is T with n minus 1 degrees of freedom. So n in this case was 20. N is 20 in this example. So this is T with 19 degrees of freedom. So please could you go to the O1 column in the T table, but this time don't go to the last row where you see 2.326. I don't want that. I want the 19 degrees of freedom row on the T table. Are you following what I'm saying? Don't go to the bottom because it's not a Z anymore. It's a T distribution. So can you please get me T 0.01? Yeah. I'm sorry, 2.539. Do we agree with this number? Okay, so this is T 0.01. That's the only thing that's going to change. So now I know how to finish up my problem. I'm here. X bar, I'll put it in here. X bar is 100 plus or minus 2.539. S was found to be 3. And rad n is rad 20 because my sample had 20 in it. All I'm doing is plugging in the numbers that they gave me, right? 100 plus or minus 2.539 times 3 over rad 20. Would you please find me E? It's still called E. Yeah?
1.703.
1.703. Are we in agreement? So I'll just call it 1.70 if you don't mind. It'll make it easier for me. So 100 minus 1.7 is 98.3. Left end point. Right end point, 101.7. If I asked you for the length, let me call this left because I'm going to call the length L. Left, right. The length, of course, is 2e. Always. The length is always 2e because I have always started at X bar and gone e to the left and e to the right. So the length is always 2e. Get it? It's not hard at all, right? Are you getting it? The only part that you have to do is put the data in your calculator and figure out the X bar and the S if they don't give it to you. Once you do that, you go to n minus 1 degrees of freedom row instead of going to the last row. So I just want to mention what is this T variable. You know how you had Z equals X bar minus mu over sigma over rad n? Remember this? T is the counterpart of this formula. T equals X bar minus mu over S over rad n. So anytime you're dealing with S, you will deal with T. n minus 1 degrees of freedom. Follow? That's why I'm able to switch my z's to t's, because now I'm dealing with s and it's a different distribution. Any question? Let's see if we can do some examples from here. How about page, I should have numbered these pages. My pages aren't numbered. Are yours? Let's number these pages, okay, once and for all, so that we can refer to them. 1, 2, 3, 4, 5, 6, 7. All right. So I want to do the example on, both the examples on page 5. It says Walter jogs 3 miles each day. He keeps records over 90 days of the time it takes to jog. Looks like n is 90. Sample size 90. The mean over 90 days is 22.5. X bar 90. Sample mean is 22.5 minutes with a standard deviation of 2.4 minutes. S equals 2.4 minutes. Why do I call it S and not sigma? Yeah, sample. It's coming. This is from the 90-day sample. So therefore, it is S and not sigma. Does that make sense? That's the first thing you have to distinguish in your problem. Are they giving you sigma or are they giving you S? They gave me S. They didn't give me his jogging time over 90 days in raw data. They did this already. S equals radical xi minus x bar square over n minus 1. This has already been done, and that is that number, is what they're saying. Follow? Let mu be the mean jogging time over the whole year, which of course is unknown. Mu unknown, because the whole point of doing this is to find an interval estimate for an unknown mean, right? So this is confidence intervals for mu, because mu is unknown. A, find a point estimate for mu. Well, a point estimate for mu is always x bar n. Always, always. So x bar n is the point estimate, which is equal to 22.5 minutes. Actually, in this case, it's x bar 90. That's the one number that estimates mu. Part B. Please note that part B is below part A, not on the side, okay? So we're doing part B. Find a 95% CI for mu. 95% confidence interval. Nice and simple. Take the 95, put it in the middle. That means 0.25 here and 0.25 here. Right? Let's go to our T table and look up 89 degrees of freedom. It's not going to be there, is it? N minus 1 is 89, right? It's not there. What is there? Do you have a 60? Is that the next lower one? Okay, so N minus 1 equals 89 is not on the table. So go one lower, one row lower than that, which is 60 degrees of freedom. That's the best I can do because I don't have that number for 89 degrees of freedom. Follow? So you always go down. So can you get me the number for, let me label this T 60 because 89 wasn't there. T 60, and can you get me this number? 60 degrees of freedom. Can you get me the number? Yeah. Even?
Yes.
Wow. Okay, 2. So this is minus 2. So I'm ready to plug in. X bar, which is 22.5, plus or minus T alpha over 2, which is 2, S, which is 2.4, divided by rad 90. I don't know if I did this. I don't know if I have an answer. Can you find me an E, please? This is my margin of sampling error, E. How much is E? Hello? .507? I'm sorry, how much? 506. So 0.51. E is 0.51. So 22.5 minus 0.51 gives me 21.99. And 22.5 plus 0.51 gives me 23.01. So we are 95% confident that Walter's true jogging time lies in this interval. Get it? Part C. Find a 99% CI from you. The only number that's going to change is this number 2, right? So 99, put that in the middle. Split the 1%, 005, 005. Can we go to T 60 degrees of freedom and 005? .66. So that's the only number that's going to change. So it's going to be 22.5, which is X bar, plus or minus 2.66 times 2.4 over rad 90. You'll find a new E and you'll finish up the problem. It's no big deal from here, right? What's your new E? .67. So 22.5 minus 0.67 is what? 21.3383 and 23.17. 17? Thank you. Done. It got wider. Confidence level went up, it got wider, right? Any question?
Beginning of the problem, what sort of indicators you look for to distinguish between if you have S or S?
Yeah, that's the most important thing. You have to distinguish whether they're giving you sigma or whether they're giving you S. So when they give you sigma, it has nothing to do with the sample. It's unrelated to the sample. So it'll say the population standard deviation is blah, blah, blah. But it didn't say that. It said Walter's mean jogging time was 22.5 minutes with a standard deviation of 2.4 minutes. That means that the 2.4 minutes was obtained from the sample of size 90. That means it's S, not sigma. Get it? So that's the most important thing, otherwise you're going to use the wrong line from the table. Okay, I want to show you how to do this on the calculator. Although the calculator answer is not going to exactly match, right? Because the calculator is going to actually look up 89 degrees of freedom. We just don't have that number on our table. Let's learn how to do it on the calculator first. Let's learn how to do it with, I'll go back on the slides, with a number that is on the table so that we're not confused. Let's go back to this problem. I'm looking for the 98%, it's just the previous page. 98% CI for mu. X bar was 100. S was 3. N was 20. Okay, I want to do this problem on the calculator. So I'm going to go to stat. Oh, it's not dark enough. Stat test T interval. Can you do it with me? I'll wait for you. Stat test T interval. It's going to ask you, are you giving me raw data or are you giving me statistics? Looks like the statistics have already been found, right? I didn't find this 3 by using the S formula. It didn't give me it didn't give me 20 values. It gave me the X bar and the S already computed, right? Is it asking you data or stats? Okay, so you're going to say stats, because data would imply that it's giving raw data, which would have to go into a list, which will be the next problem that I do, okay? So stats, then it's going to ask for what? Hello, what is it asking for? Hello? X bar, the mean? Okay, so X bar equals 100. What else? S? N? S what? S. S equals 3. N equals 20. Is it asking for confidence level? Okay, so going to put in 0.98 is the confidence level. And I want to make sure that I get an answer similar to what I got when you hit enter. What is it? 98.296.
101.7.
101.7. Good enough, right? So this is what I'm trying to say, is that if you do this problem, the next problem that we did, on the calculator, it may not match up well enough because this one was great. This one was a perfect match to what we did by hand. Same, right? But it may not be the case for this problem because I was using 60 degrees of freedom and the calculator is capable of using 89 degrees of freedom. Follow? So let's do stat, test, T interval, data or stats? Raw data or stats? Stats, yeah. Raw data would be a string of numbers that you have to input. That's not the case here. X bar equals 22.5. S equals 2.4. N equals 90. And the confidence level is 0.95. The number is going to be slightly different, but not horribly different because the difference in the rows between 89 and row 60 wouldn't be that much. Okay? So what answer does it give? 21.997?
Yeah.
Okay, this is what I mean. Not horribly different. Even though I used 60 degrees of freedom and they used 89 degrees of freedom. Get it? Because as you go down that table, right? Look down any column of the T table. The difference between the numbers starts getting minuscule as you approach the Z value. Okay, and what's this number?
23.003.
Okay, so you see how it's no big deal, right? You're still going to pick, I would pick this on a multiple choice test, no problem. Because the other choices are going to be nothing like that. Yes? Question? No, sorry. All right, I want to do the next one, which is still page 5. Given the following 8 values from a sample, lecture 4, page 5, bottom. This is page 6. Given the following 8 values, okay, n equals 8. Find the 95% confidence interval. 95%. Okay, so this time they're giving me raw data from the sample. Data, not stats, right? I have to find my own X bar and my own S, which I'm not even going to bother to do because if I just put this data into L1, the calculator will do everything automatically. So just go to Stat, clear list L1 and hit enter. First I want to clear my L1 so I can go input the data into L1. Then stat edit, and then go put into L1 all this data. 14.26 ... 14.94. Put those 8 values into L1. Go ahead, I'll wait. Okay, once you've done that, then you're going to go to stat, test, T interval. I'm still doing T interval, not Z interval, because I don't know sigma, right? When I know sigma, I use Z alpha over 2. When I know S, when it's about S, I use T alpha over 2. Does that make sense to you? Okay, so stat test T interval, this time it's data. Not stats, it's data. We're providing the data. Is it asking you for which list? L1? L1 is the list. Does it have frequency below that? So just put in 1. Because every point was put in individually, right? Then what? Then what does it ask for? Confidence level? 95. Then what? Calculate. So what does it give you? Answer? 12.476, comma? 15.691. It's as simple as that. Something's wrong with your data. Did you put in 0.95 for the confidence level? You did? Okay, then you want to check this list. So go to stat edit and make sure that the list was put in properly, because clearly something got tweaked. Do you get it, guys? Okay, good. Let's see what else we need to do.